The paper presents a novel approach to accelerating deep neural networks on field programmable gate arrays, FPGAs, using a hybrid compression scheme. Existing compression methods, such as pruning and quantization, are insufficient due to limited memory bandwidth and computing resources. The authors propose a hybrid compression scheme combining filter pruning, weight quantization, and knowledge distillation. Filter pruning reduces memory requirements and computation overhead by decreasing the number of filters in each convolutional layer. Weight quantization further reduces memory usage and improves computational efficiency by changing weights from 32-bit floating-point numbers to 8-bit integers. Knowledge distillation involves training a compressed model to mimic a pre-trained, uncompressed model using a distillation loss function. The authors formulate the compression problem as an optimization problem, minimizing the loss function subject to memory usage and computational resource constraints. The optimization problem is solved using an ADMM algorithm variant. The proposed scheme is evaluated on ImageNet and CIFAR10 using ResNet 50 and VGG16, achieving significant reductions in memory usage and computation overhead while maintaining comparable accuracy to uncompressed models. Accelerating long short-term memory (LSTM) neural networks is crucial for high-rate dynamic system models, particularly in real-time structural health monitoring applications. The DROPBEAR dataset serves as a benchmark for evaluating models that take vibration data as input and output the initial conditions of the cantilever beam. LSTM networks have proven effective in capturing dependencies for long sequential or temporal data, with applications in speech recognition, natural language processing, and image captioning. In high-rate dynamic systems, LSTMs can infer the state of a structure in real time, making them suitable for ultra-low latency state estimation applications. To achieve rapid response times, a hardware-based LSTM model is developed to meet the sub-millisecond or microsecond scale requirements of high-rate dynamic systems. A three-layer LSTM architecture is designed and trained offline using logs recorded from the physical DROPBEAR apparatus, achieving acceptable accuracy in terms of signal-to-noise ratio and desired latency on a real-time operating system, RTOS. However, the RTOS is unable to exploit the available parallelism within LSTMs, making field programmable gate arrays, FPGAs, a suitable alternative for LSTM implementation. The paper contributes to the design of an LSTM accelerator framework using high-level synthesis, HLS, that meets real-time requirements. An alternative approach using hardware description language, HDL, is also presented to improve performance. The authors investigate model deployment on several FPGA platforms to determine the best performing configuration given the application. The results show that the HDL approach provides flexibility in choosing the level of parallelism based on available resources and timing requirements, which is not possible with the HLS-BASED approach. The Xilinx Alveo U55C platform achieves the lowest latency of 1.42 microsiemens and the highest throughput of 7.87 Gops for the HDL design, making it the most suitable configuration for high-rate dynamic system applications. For high-rate dynamic systems, selecting an optimal long short-term memory (LSTM) model configuration is crucial for accurate prediction and efficient processing. In this study, a specific LSTM model was chosen for its ability to effectively capture complex temporal relationships. The experimental data used consisted of high-frequency time-series data, which was used to train and evaluate the LSTM model. The chosen LSTM model configuration consisted of 256 units per layer and 4 layers, which provided an optimal trade-off between model accuracy and computational complexity. This configuration enabled the model to capture both short-term and long-term dependencies in the data, resulting in improved prediction performance. To accelerate the LSTM model, a custom hardware accelerator was designed and implemented using the Vitis High-Level Synthesis (HLS) tool. The accelerator architecture comprised 2 primary units, a matrix vector operations unit and an elementwise operations unit. The matrix vector operations unit performed matrix multiplications and vector additions, while the elementwise operations unit handled sigmoid, tanh, and other elementwise functions. This design enabled the accelerator to efficiently process the LSTM model's complex computations. The experimental results demonstrated the effectiveness of the chosen LSTM model configuration and the custom accelerator design. The accelerator achieved a significant reduction in processing time and energy consumption compared to software-based implementations, making it suitable for real-time processing of high-rate dynamic systems. The authors discuss the implementation of an LSTM accelerator on an FPGA platform, focusing on the partitioning and pipelining of the design. They partition the input, hidden state, and bias vectors to create registers, enabling parallel access, while storing the weight vectors in BRAMs due to their large size. The input and hidden state vectors, as well as the input and recurrent weight vectors, are concatenated to facilitate multiplication and accumulation operations. Pipeline pragmas are applied to the outer loops of the functions to enable fully pipelined operations, with the internal loops not fully unrolled due to BRAM limitations. The RTL implementation of the LSTM is described, providing more flexibility than HLS. The design consists of modules, including gate modules, multiplier, adder, and activation functions, which are instantiated multiple times for parallel execution. The number of instantiations can be configured for adjustable parallelism. Weights are stored in separate BRAMs for each hidden unit, and registers are used for parallel data access. The overall system design is presented, consisting of a custom IP block for the LSTM accelerator, which can be exported from HLS or built directly with HDL. External block RAM generator modules are used for storing inputs, weights, and outputs, fetched from external DDR3 DRAM or high bandwidth memory, HBM. Differences in memory access between the VC707, ZCU104, and U55C boards are highlighted. The experimental setup consists of 3 platforms with varying levels of parallelism, connected to a host PC via a USB JTAG interface. These platforms evaluate the performance of a long short-term memory, LSTM, model with 32-bit, FP32, 16-bit, FP16, and 8-bit, FP8, fixed-point precision. The results are compared in terms of maximum frequency, resource utilization, latency, throughput, and normalized throughput. High-level synthesis, HLS, designs tend to optimize themselves regardless of pragmas in different platforms and bit precision. Despite the reduction in resource usage and increase in frequency for FP8, the model did not automatically utilize the freed-up resources to decrease the delay. To further reduce latency for FP8, the design must be updated again. The effects of pipelining and unrolling the outermost loop inside each gate are compared in Table I. Unrolling the outermost loop entirely or partially did not enhance performance significantly, even though resource use, such as DSP, increased by 8 times. In contrast, the number of DSP blocks can be controlled in HDL design, allowing for increased parallelism. However, this leads to congestion in the routing system, reducing overall frequency and occasionally resulting in no routing at all. The results in Tables 2, 3, and IV indicate that after 32-bit precision, HLS design starts performing better than the HDL design. Full parallelism can be achieved for the LSTM model up to 16-bit precision in all FPGA platforms except ZCU104, which exceeds available DSPs if more than 2-unit parallelism is applied. With full parallelism, U55C achieves the lowest latency of all, as shown in Table 2. For HLS design of FP8, DSPs were only employed for the activation functions because DSPs are not used below 10-bit precision. Although the use of DSPs for multipliers in HDL design was compelled, their proper sharing could not be obtained, which would have reduced consumption. The total number of operations was determined for the LSTM model, from which the throughput was computed. Normalized throughput was calculated with respect to LUTs and DSPs for a fair comparison between HLS and HDL-based design. HDL design has the flexibility to increase resources to maximize throughput, resulting in higher throughput than HLS design in all platforms. The authors present the results of their high-level synthesis, HLS, and hardware description language, HDL, designs for a long short-term memory, LSTM, accelerator on various field programmable gate array (FPGA) platforms. The HLS design on the ZCU-104 platform achieves the lowest latency of 2.92 microseconds and a high GOPS of 3.83. The HDL design on the U55C board achieves the lowest latency of 1.42 microseconds and the highest GOPS of 7.87, outperforming other state-of-the-art designs. The authors conclude that their custom LSTM accelerator on FPGA, created using both HLS and HDL, outperforms other current LSTM accelerators on FPGA in terms of latency, throughput, frequency, and normalized throughput. The paper presents a novel approach to understanding the complex interplay between quantum mechanics and general relativity, two fundamental theories in physics. The authors propose an innovative framework that integrates these seemingly disparate fields, offering new insights into the nature of spacetime and matter at the quantum level. Quantum mechanics, which describes the behavior of particles at the atomic and subatomic level, is fundamentally incompatible with general relativity, Einstein's theory of gravity. This incompatibility has long been a source of frustration for physicists seeking a unified understanding of the universe. The proposed framework, dubbed quantum gravitodynamics, posits that spacetime is not a passive backdrop for physical events but rather an active participant in shaping the behavior of particles. This idea challenges the traditional view of spacetime as a fixed, unchanging entity and instead suggests that it is dynamic and responsive to the presence of matter and energy. Central to this new paradigm is the concept of quantum entanglement, where pairs of particles become interconnected such that the state of one particle instantly affects the state of its partner, regardless of the distance separating them. The authors argue that this phenomenon can be used to probe the nature of spacetime itself, revealing its intricate structure and dynamics. In addition to theoretical developments, the paper also outlines potential experimental methods for testing the predictions of quantum gravitodynamics. These include high-precision measurements of gravitational waves, which are ripples in the fabric of spacetime predicted by general relativity, and observations of quantum entanglement phenomena in extreme environments, such as near black holes or during the early universe. While the proposed framework is still speculative and requires further refinement, it represents a significant step forward in the quest for a unified theory of quantum gravity. By bridging the gap between quantum mechanics and general relativity, quantum gravitodynamics offers a promising avenue for advancing our understanding of the universe and the laws that govern it.